Hello! In this video, we are going to derive the power rule for derivatives using the binomial theorem. Now, let's start out by writing the definition of a derivative. Right, so this is the definition of a derivative, right? We have the derivative of some function f of x. Turns out all it is this limit. Now, really, in our case, our f of x is really x to the n. So let's just replace f of x with x to the n. Okay, so then what's f of x plus h? Turns out all that is we are replacing the x here with x plus h. Right, so just like that. And of course, we have minus f of x, which is just x to the n, and then divided by h. So this is the limit that we want to evaluate. And we want to get the binomial theorem involved. But what is the binomial theorem? If you recall, the binomial theorem goes something like this. This is the binomial theorem. And really, it looks a little weird, but all it's saying is it's telling you how to expand something like this. For instance, you could expand this by hand. You would be multiplying x plus 3 by itself 5 times. You would be distributing across a lot of things, right? But it turns out once you've completely expanded this out, it's going to be exactly in the form described by this sum. And that's really the whole idea. Now, another thing is, what is this thing? What is nk? It turns out all this notation is n factorial divided by k factorial times n minus k factorial. That's really all that this is. And so yeah, this right here is the binomial theorem. And we're going to apply it to what we have in this limit. And it turns out we can actually apply it right now because we have x plus h to the power of n, which is precisely in the form of a plus b to the power of n. So really, all we're going to do is we're going to rewrite x plus h to the power of n using this summation. Really, all we're doing is we're replacing a with x and b with h. And so this is what we get when we do that. So now at this point, what we want to do is we want to manipulate what we have here in some sort of way so that we can evaluate this limit as h approaches 0. Okay, so then we just sort of have to play around with it. It turns out we can actually eliminate this x to the power of n. The way we can do that is by realizing that the first term in this sum is precisely x to the power of n. That is, when k equals 0, this term is x to the n. And to see why, let me expose the term when k equals 0. And then we'd be adding on everything else, right? We would be adding on what happens when k equals 1, then what happens when k equals 2, and so on all the way up to k equals n. Right, so just like that. And then, of course, we're still subtracting the x to the n, and we're still dividing by h. Now, notice, as I said before, this first term is precisely x to the n. And to see why, of course, h to the power of 0 is just 1. But it turns out n0 is also 1. Technically, it's n choose 0, if you want to say it correctly. And to see why n choose 0 is just 1, it's really just taking what we have here and replacing k with 0. It turns out that 0 factorial is just 1, so we don't even have to write this. And n minus 0 is just n. So we have n factorial divided by n factorial, which is, of course, just 1. And so, yeah, n choose 0 is precisely 1. Of course, x to n minus 0 is just x to the n. So really, we have x to the n minus x to the n. So those two things go away, just like that. And so now that we have that, really all we have now is this sum divided by h. And I'm actually going to rewrite this in a different way. I'm going to write it as 1 over h times this sum. And so this is really what we get. Now, as you may have suspected, we can actually move the 1 over h to the inside of this sum. The reason why is because this sum is taken over the variable k. As k varies from 1 to n, h doesn't change. So h is treated as a constant with respect to this sum. So we're allowed to move the 1 over h to the inside of it. And the reason why I moved the 1 over h to the inside of this sum is because we see now that we have h to the k divided by h. But of course, h to the power of k divided by h is just h to the power of k minus 1. So let's rewrite that, moving up to the top. Right, so now we have rewritten h to the power of k divided by h as h to the power of k minus 1. And so now at this point, we are just about in a position where we can evaluate this limit. And to see why, what I'm going to do here is I'm going to expose some of the terms in this sum, right? I'm going to expose this sum when k equals 1, when k equals 2, when k equals 3, and so on until k equals n. So this is what I've done. I have re-expressed this sum by exposing some of the terms, right? I've rewritten the sum for k equals 1, k equals 2, k equals 3, and so on until k equals n. And next, what I'm going to do is I'm just going to simplify these terms up a little bit. So this is what we have when we just simplify this up a little bit. But notice what happens. Every single term has h to the power of some positive integer, except for this one. So notice we have h to the power of 1, h to the power of 2, and we keep going, we're going to have h to the power of n minus 1. So notice when we take this limit as h approaches 0, this term becomes 0. This term also becomes 0, and so on, this term becomes 0. The reason why is because when we take the limit as h approaches 0, we can now do direct substitution. We would have 0 times this, 0 squared times this, 0 to the power of n minus 1 times this. They would all become 0 except for this term, because this term doesn't have h in it. So now, when we take the limit as h approaches 0, all we're left with is this term. So really, this is what we're left with. And now all we have to do is evaluate what n choose 1 is. All we're doing is we're replacing k with 1. Of course, 1 factorial is just 1, so we don't even have to write that. And I'm actually going to rewrite n factorial as n times n minus 1 factorial. Because n factorial is precisely equal to this. So now it's easy to see that the n minus 1 factorials go away, and so all we're left with now is n times x to the power of n minus 1. And so this is our final answer. And so yeah, that's pretty much how you could derive the power rule for derivatives using the binomial theorem. And yeah, that's pretty cool. We get the derivative of x to the n is n times x to the power of n minus 1. Exactly what we wanted. And so yeah, that's pretty much the idea of how you can do it. So yeah, that's pretty much it for this video.